Hey, grade 10s. So today we're going to go over our first lesson of Unit 4, which is integer exponents. So the first few slides I'm going to go through a little bit faster just because I know that it's mostly review. We're really just going over exponent laws. So I just want to skip over to the top for examples when we start looking at powers that have negative exponents. This is where it gets a little bit different. But hopefully most of the lesson you'll find pretty reasonable to go through. So first of all, what are exponential functions? So we obviously are going to talk about this in more detail later on, but I figured the first thing I wanted to just kind of discuss is how exponential functions are special, really what makes them distinct. So we're obviously in a new unit. You probably noticed that the first two units really, I almost want to say is kind of setting up what we're going to be doing for the rest of the course, especially the first unit's an introduction to functions. And then the second unit was really more working with the algebraic skills that we need to succeed. And unit 3 focuses on quadratic functions. Unit 4, we're now focused on exponential functions. I think everyone has already started to realize the whole theme of the entire course, functions. We're learning about different types of functions and what makes them distinct and special. So in Unit 4, we're going to focus our attention on exponential functions, which themselves have a lot of special features. So what really makes them stand out from compared to other functions is that their relation changes multiplicatively. So it's not actually going to be changing by adding a certain amount each time, or even finding a constant second difference. What we notice is that the y values will be multiplied by the same value over and over again. So as an example, you could have a relationship that keeps doubling or tripling or quadrupling, whatever it might be. So an example of a world, something that is exponential would be a world population. It grows by a certain percent each time. So every single year it might grow by 2% or 3%, whatever it might be. And that's the amount that it keeps increasing by each time. So it's not like we're adding that percentage, we're actually multiplying by that percent. And it's kind of interesting to go over exponential functions because there's a nice little tie-in with financial math. And financial math, we don't really talk about functions per se, but a lot of those ideas in financial math stem from this. So it's really good that you start to understand it now. So quick little review, parts of a power. I'm sure everyone already knows this. When we refer to the base, we're referring to the number that is being multiplied, and the exponent is simply referring to how many times we multiply by that base, that base by itself. So really, the powers are just, instead of just like multiplication is repeated addition, while powers are simply repeated multiplication. That's really what you're doing there. Really important that you understand these terms. I will use them a lot. So when I talk about the base of the power, I'm talking about the large number, the one we're multiplying by, and exponent is how many times we multiply. So quick recap, exponent laws. So we know how to simplify powers with at least a positive integer exponent. And specifically whole number, right? We want to just make sure you understand that we're just looking at whole numbers right now. So some examples of exponent laws we already know. We know that if we multiply powers with the same base, and again, with the same base, key word there, key expression there, then we know that we can add the exponents. If we divide powers with the same base, we simply subtract the exponents. And if you need a little recap as to why we do this, I don't want to go into too much detail. I kind of skipped that explanation because I assume that everyone learned that in grade 9. But essentially, it kind of makes sense that if I give you something like 2 to the power 3, and then I multiply by 2 to the power 4, what this is really saying is you have 2 times 2 times 2. And what this is really saying is you have 2 times 2 times 2 times 2. And really, in the end, if I'm asking you how many times am I multiplying 2 by itself, I'm multiplying it by itself 7 times, right? So it makes sense that I would simply add the exponents. And same with division. It would also make sense that if I had something like 2 to the power 4 divided by 2 to the power 3, well, really what I'm saying is I have 2 times 2 times 2 times 2 divided by 2 times 2 times 2, which is actually, again, I love when there's little nice connections to what we just did. In Unit 2, we talked about rational functions and how we can simplify them. It's actually very similar to what we are doing here. We kind of notice that if we have powers with the same base, if we're dividing them, then you can simply subtract their exponents. So I'm hoping that ties in really well with what we just covered in Unit 2. And then if we have a power to a power, we know that we can simply multiply the two exponents. And again, that should also make sense that if I'm raising a power to a power, then I'm multiplying that power by itself over and over again, which really just means I'm multiplying the exponents. And of course, a product raised to a power, we kind of know this from grade 9, and we definitely have talked about this when we talked about algebraic expressions. You have to apply that exponent to the to both parts of the product, right? So to both factors. So if I had something like 4x squared, although I think everyone knows this now, you apply the exponent 2 to the 4 and you apply it to the x. So it becomes 4 squared x squared, which becomes 16x squared. So these are all just exponent laws that you've learned before. I'm hoping you're familiar with them. A quotient raised to a power, what that really means is that this simplifies into, that means that we have to apply the exponent to the numerator and the denominator, right? You can also think of it as fractions. So we apply it to the numerator and the denominator, which basically means I have a to the power of n over b to the power of n. So again, another example, if you want a concrete example, 3 over 4 raised to the power of 5. That just really basically means I applied the 3 to the numerator and the denominator, and I have something like this, right? And then I just have to figure out what each of these parts are. I'll leave that to you to do, okay? And then, of course, we also know one really special property, that a to the power of 0 is equal to 1. I don't want to go over why that's the case. Again, that's hopefully something you remember from grade 9. Hopefully your grade 9 teacher went over that. It is a really special property. So anything raised to the power of 0 is 1. So the most important thing, where are the negative integers, right? We didn't actually talk about negative integers. So that's actually going to be our focus in this lesson, is how to deal with powers that have negative integers. So before we get to that, let's just do a couple quick examples here. I'm not going to go into much detail. If I ask you to simplify this, I have to apply the exponent 2 to the first factor in the product, and then I have to apply it to this power right here, x cubed. And so then I end up getting 4 squared x cubed squared, and that becomes 4 squared, which is 16, and then x cubed squared is 6, because I simply multiply the two exponents there. If I ask you to simplify this one here, so we take 2 and raise it to the power of 4, and then we take 5, raise it to the power of 4. That gives us 2 to the power of 4 over 5 to the power of 4, which you could leave as that. Or if this is, to be honest with you, it's reasonable. I guess you could calculate what it is. So 2 to the power of 4 is 16, right? So 2 times 2 times 2 times 2. 5 to the power of 4 would be 625. So you could calculate it, but I'm normally pretty flexible. I'll kind of let you know if I want you to actually evaluate it or just leave it or simplify the power. So again, if I say simplify, that means just simplify it and reduce it as much as you can. If I actually, so you're basically applying the exponent laws. If I ask you to evaluate, it means you have to give me the number. Last one here. The last one's going to involve a couple different rules. So we have a product of two powers, and then we're going to be dividing. Okay, so you want to multiply first and then divide. So when we multiply, we know that this ends up giving us 3 to the power of 12, and then we have 3 to the power of 12 divided by 3 to the power of 7, which a different way that we could approach this is we can simply add the exponents and then subtract the 7. And that would give us 3 to the power of 5 in the end. Here's a couple more examples. So if we have multiple operations, you want to be careful that you simplify power to a power first. It's just like that math, right? You always want to do power to power first before you multiply and divide powers, and you're going left to right. With fractions, though, you have to be really careful with this. It's really important that you simplify the numerator and the denominator first, and then you divide the numerator by the denominator, okay? Otherwise, you will follow BEDMAS if there's brackets, right? So we know that we're always following BEDMAS, and really the reason you're doing that is because when you have a fraction, you don't necessarily see it, but really what the understanding is that there is technically a bracket around the numerator and the denominator separately, right? So you want to figure out you want to simplify the numerator first, then simplify the denominator, and then after you do that, you want to divide the numerator by the denominator. That's really what you're doing. So here's an example just to practice. So we have a power to a power. So I'm going to figure out what that is first. And then I'm going to simplify the denominator here. So I'm going to do this in red. So a power to a power, this gives me, this means I multiply the exponents. So I'm going to have 7 times 3. And then in my denominator, I'm going to have 8 to the power of 9 plus 10. So this ends up giving me 8 to the power of 21, because I simply just multiply the two exponents there. And then in the denominator, I add the two exponents because I'm multiplying. And then my last step here is I simply take 8 to the power of 21 divided by 8 to the power of 19. I have to subtract the two exponents, and I end up getting 8 squared, and I'm done. Here's another example. I have 5 to the power of 14 divided by 5 to the power of 4 times to the power of 2 times 5 to the power of 3. All right, so this one was a little bit messy, but let's take it step by step. I'm going to simplify. There's nothing to do in the numerator. I'll leave it alone. I'm going to simplify the denominator. So I have 5 to the power of 4 to the power of 2, which is 5 to the power of 8. And then I multiply by 5 to the power of 3. And so in my next step here, I notice that since I'm multiplying the two powers, that means I can add the two exponents, right? So when you multiply powers with the same base, for the cube part there, you simply add exponents. So then I end up getting 5 to the power of 14 divided by 5 to the power of 12. And then the last step here, I simply subtract the two exponents, and I end up getting 5 to the power of 3. So hopefully that's making sense so far. So how do we deal with negative exponents? So with negative exponents, the whole idea here is that you work with the reciprocal of the base. So what you're going to do is you're basically going to switch the numerator and the denominator, right? Remember, the reciprocal of a base is basically, the reciprocal of a number is basically the number we have to multiply by to get to 1. So really what you're doing there is simply switching the numerator and the denominator, right? You switch their position. So note that the reciprocals of two numbers that, like I said, are two numbers that multiply together to give us a product of 1. So as an example, the reciprocal of 4 would be 1 over 4. The reciprocal of 2 over 3 would be 3 over 2. And you can even check yourself. 4 times 1/4, it gives us 1. 2/3 times 3 over 2 gives us 1, right? So that's really what a reciprocal is. So if I want to evaluate what this power would be, well, what I'm going to do here first is I'm simply going to take the reciprocal of 4. So the reciprocal of 4 is 4 to the power of -1. We almost want to think of it that way. And again, remember, we discussed terminology, right? So don't confuse this with inverse functions. I know that it's a little bit confusing, right? An inverse function, like I said, that's not the same thing as a reciprocal. So just don't get that confused. I know the terms are sometimes a bit confusing. As I mentioned already, the reason we call it an inverse function is because it is basically the function that will undo the original function, right? Which is kind of what you're doing with the reciprocal of these numbers. If I have something like 4, and then I'm thinking, oh, if I want to get back to the 1 value, I would have to multiply by 1/4 so that I end up back at 1. So imagine if you had a calculator, you multiply by 4 by mistake, and then you're like, oh shoot, I want to go back to the 1 that I had, or whatever number you had. You simply would multiply by 1/4 to get back. So that's really what we're doing here. We're realizing that to find the reciprocal, all we're really doing in this case is simply writing it as 4 to the power of -1. Now notice here that 4 to the power of -3 is actually rewritten or decomposed, you want to think of it that way, as -4 to the power of -1 to the power of 3. So why are these expressions the same? Well, you can even use exponent laws. You know that if I have a power to a power, I simply multiply the exponents. So 4 to the power of -1 to the power of 3 is actually the same as 4 to the power of -3. So what I do next is I notice that 4 to the power of -1 is simply just the reciprocal of 4. And obviously the reciprocal of 4, we already talked about this, is 1/4. And we know that because 1/4 times 4 gives us 1. And now we have 1/4 to the power of 3. So how do I evaluate this? Well, this is actually pretty easy. All I have to do is simply apply the exponent 3 to 1 and apply the exponent 3 to 4, the numerator and the denominator. And what I end up getting is 1 to the power of 3 divided by 4 to the power of 3. And obviously 1 to the power of 3 is 1, 4 to the power of 3 is 64. So I end up getting 1 over 64. So what's the general rule here? The general rule is that if I have a power with a negative base and an integer, so either a whole positive or whole negative number, it's going to be equal, and an integer is equal, so a power with, I'll also repeat that again, power with a negative exponent and an integer. And I think I made a mistake here, sorry, a negative exponent. I totally made a mistake here, so I'll rewrite that. And what I meant to say is an integer exponent. That's going to be equal to the reciprocal of the base raised to the opposite exponent. So basically what I do is I find the reciprocal of the base, right? So I'm going to find the reciprocal of the base and then I raise it to the opposite exponent. So I switch the sign of the exponent. Okay, so that would be a negative exponent, the negative exponent to the positive exponent, right? So what I mean by that is, so if I have this power, so I'll kind of explain this, what I mean by this algebraically. So if I have a negative exponent here, negative n, and an integer base, right? So this is an integer base that I'm looking at. So in this case, I have like I said, I have a whole positive or negative number. This is going to be equal to the reciprocal of the base raised to the opposite exponent, right? So what I notice is that this a right here is basically just going to switch to 1 over a. I find the reciprocal of it. And then instead of raising it to a negative exponent, now I just raise it to a positive exponent. And then what we notice is that if I take 1 and I raise it to the power of n and a to the power of n, it actually simplifies to something easy. 1 to the power of anything is going to be 1, and a to the power of n is just a to the power of n. So I end up getting 1 over a to the power of n. So I simply have to switch the numerator and the denominator, and then I raise it to a positive exponent after. So here's an example. I have 5 to the power of negative 3. So what I'm going to do is, I got another one there, and then I have negative 3 to the power of negative 4. So for the first one, 5 to the power of negative 3. So what I'm going to do is I'm going to take, again, I'm going to think about the reciprocal. So the reciprocal of 5 is 1 over 5. And then what I'm going to do is instead of raising 5 to the power of negative 3, I'm going to write that as 1 over 5 to the power of positive 3. And then I'm going to simply apply the exponent to 1 and apply the exponent to 5. But we know that 1 to the power of anything is 1. So then we end up getting 1 over 5 to the power of 3. And 1 over 5 to the power of 3 is just simply going to, we can leave it like that, or we can actually simplify what this actually means. 5 to the power, we can actually evaluate this. 5 to the power of 3 we know is 125, so we can leave our answer as 1 over 125. So once again, I'll repeat that again. We simply find the reciprocal of the base, right? So find the reciprocal of the base and then raise it to the opposite exponent. So instead of it being raised to the power of negative 3, we're going to raise it to the power of positive 3. And then again, you simply apply the exponent to the numerator and denominator. But again, 1 to the power of anything is just 1, so it's not very special. And then in the denominator, we have 5 to the power of 3, which is 125. So this is correct. So I hope that kind of makes sense so far. All right, let's look at another example here. We have negative 3 to the power of negative 4. So I think what throws people off is the fact that it's negative. It sometimes seems a little bit tricky, but let's work through this step by step here. So negative 3 to the power of negative 4. Again, we're going to follow the same idea here. We know that this would be equal to the reciprocal. So the reciprocal of negative 3 is going to be negative 1 over 3. And don't confuse this with negative reciprocal, by the way, right? Sometimes people get it confused. It's just the reciprocal. We're not switching the signs. So the reciprocal of negative 3 is negative 1 over 3. Again, it makes sense because you can do the math yourself. Negative 3 times negative 1 over 3. I get a positive answer, and we know that it's going to be positive 1. So negative 1 over 3, it's going to be raised to the power of 4. So instead of having negative 3 to the power of 4, I simply take my exponent and I replace it with my negative exponent, I replace it with the positive. I replace my whole number here with a fraction there, right? So it's simply going to be the reciprocal of the base. And now I have negative 1/3 to the power of 4, which you could obviously solve by doing, you could do negative 1 over 3 times negative 1 over 3. This isn't a very efficient way to do this at all, and I don't recommend it. But you could technically do this. You can multiply negative 1 over 3 4 times, or you might realize a bit of a shortcut. You can still apply the exponent 4 to the numerator and the denominator. Now, one thing you want to be careful of is the negative sign. So if I have a negative number and I multiply by a negative number a total of 4 times. So if I have 4 negative numbers and they're being multiplied, what will the sign be? Well, hopefully you remember the rules here. A negative times a negative is a positive. And then we know that positive times a negative gives me a negative. And then I know that if I multiply by another negative, so it's a total of 4 negatives, while my previous answer with 3 negatives was negative. And now if I take a negative times another negative, I actually end up back at a positive. So the general rule with when you're multiplying negative numbers over and over again, we notice that we switch from positive, negative, negative, positive, negative, positive. So in the end, we know that this answer will be positive. So we don't technically have to worry about whether the negative goes in the numerator or if it goes into the denominator. It doesn't actually really make a difference, to be quite honest. You can either put the negative in the numerator or the negative in the denominator. I personally would say, put it in the denominator in this case, because really the one being negative won't affect it as much. So we can just put the negative in the denominator. It doesn't really make a difference. In the end, your answer is going to be positive. And how did we get positive 1 over 81? Well, we simply had to raise 3 to the power 4, which we know 3 to the power 4 is 81. And that's what we got that answer there. So here's a general rule when you're dealing with negative bases. So if your base is negative, you really, really, really want to be careful with this. This is something you hopefully learned in grade 9, but I will go through it again. So if your base is negative, you really want to be careful with the sign of the power, because as I mentioned already, when the base is negative, then you're switching signs as you go along, right? So you want to be able to count, you want to be able to determine what the sign of the power will be before you actually carry out all the steps. So the rule here is that if the base is negative and the exponent is even, then the power is positive. And that should make sense, right? Because we discussed this, that a negative times a negative, we know is going to be a positive. But as soon as I have a negative times a negative times another negative, it's going to be negative. But if I have a negative times a negative times a negative times a negative, that's actually going to bring me back to a positive. So I basically go negative, positive, negative, positive. So if the exponent is even and it's a negative base, then the power is negative. And if the base is negative and the exponent is odd, then the power is negative. So a really good question is, what if the base is positive? What do you have to do? You don't have to do anything, right? Because if the base is positive, then of course your power is always going to be positive. You don't even have to check. So you only have to worry when the base is negative about the sign. If the base is positive, it's an easy piece of cake, right? You don't have to worry about it. So just a little warning here that one of your test questions, what I'll eventually do, and people always ask me this, could you have a negative fractional base, and then on top of that have a negative exponent, and then on top of that, when we learn about roots, could you have a root as well? You could have any of those combinations, right? And it sometimes gets a little bit crazy. You will see some examples that are a little out there because there's a lot of negatives, a lot of fractions involved. But again, if you remember all these rules, it shouldn't be too difficult, right? So here's an example, negative 2 to the power of 3. We know that negative 2 to the power of 3 is obviously going to be negative 8. So we multiply the negative 2 by itself 3 times. That answer will be negative in the end. Negative 4 to the power of negative 3. Again, we discussed this. We can simply write this as negative 4, negative 1 over 4. So we simply find the reciprocal of that function. Sorry, not that function. The reciprocal of that base, which is negative 1 over 4, and then we switch the negative exponent to a positive exponent. And then that means we have negative 1 over 4 times negative 1 over 4 times negative 1 over 4. And because we're multiplying 3 times, then you're multiplying an odd number of times, right? That means the exponent is odd. Then of course your power is going to be negative. And so you can just put the negative in front. And if you have something like negative 6 squared, obviously negative 6 times negative 6 is positive 36. So hopefully that makes sense. These are just a couple of small examples there. So what if you have powers with a fractional base? So we looked at bases where, it was a whole number. What if it's a fractional base? Well, if it's a fractional base, you would still follow this kind of the same way. But there's a little change you have to make, right? It's just a small change, but it's nothing too big. So what I'm going to ask you to do first is just rewrite this as a power with a positive exponent, and then we're going to evaluate. So what that means is, as I mentioned already, if I have something like negative 5/6 to the power of -2, I already learned this, that we can actually simply rewrite this as the reciprocal, right? So that I can simply put the 5/6 to the power 2 in the denominator. And then what ends up happening is I will simply apply the exponent 2 to the numerator and to the denominator. And again, just so you're clear on this is just an example, right? To kind of explain to you what the rule is, how we work with fractional base. But this is not going to be something that is going to necessarily be on a test. I'm not going to ask you to explain it, to show me two different ways, because what we're going to do is we're going to approach this problem two different ways. I really just want you to understand how to, the steps you have to carry to switch it to a positive exponent, right? So first thing we notice is obviously I'm going to rewrite 5/6 to the power -2 as 1 over 5 to the power 6 to 5/6 to the power -2. Sorry, to the power of +2. Sorry, I apologize. I know it's a lot to say there. And then, of course, this switches into 1 over 5 squared over 6 squared. And when we divide by a fraction, be really careful with this. We know that we can simply multiply by its reciprocal. So this is really what I have here. And I'm gonna go on this side. I want to make space because I know there's something coming up there. So I'm gonna multiply by 6/2 over 5/2. And then what we end up getting is 1 over 6 over 1 times 6 squared, 6 squared over 5 squared. And then we know that this just becomes 6 squared over 5 squared, which is 36 over 25 when we evaluate it. Here's a different solution. So we can approach it a different way. So instead of having 5/6 to the power -2, I'm actually going to break my exponent down there into -1 times +2. And again, why are you allowed to do that? Because of exponent laws. A power to a power means you multiply exponents. So I'm just breaking it down a little bit, right? So what I'm going to do first is I'm going to find the reciprocal of 5/6, and then I'm going to raise that to the power 2. So what's the reciprocal of 5/6? That's 6/5. And we know that 6/5 is then raised to the power 2. So what happens here? 6/5 raised to the power 2 means I have to raise the numerator to the power 2 and then the denominator to the power 2. This gives me 6 squared over 5 squared. 6 squared is 36, 5 squared is 25, so I get 36 over 25. So notice that if we actually got the same answer just in a different way. So we see here that the general rule, if we raise a fraction to a negative exponent, then we can simplify, then we can simply just find the reciprocal of the fraction. So we find the reciprocal of the fraction, and then we raise that reciprocal to the power to the positive exponent. So it's actually not that different from what we just did. The only difference is that the other examples, the reciprocal was a unit fraction. Now it's not a unit fraction. That's literally the only difference, right? But it's the same concept, okay? So the general rule, if the base is fractional and the exponent is negative, then we find the reciprocal of the base. Again, reciprocal of the base, change the numerator to denominator, and then it's going to be raised to the power to the opposite exponent. So what that means in algebraic terms is that if I have a fraction a over b, again, this just represents a fraction. I simply exchange the numerator and denominator, so it becomes b over a. And instead of raising it to the power of a negative n, I raise it to the power of positive n. So I just switch the sign as well. So I find the reciprocal of the base, and then I raise it to the opposite exponent. So instead of it being raised to a negative exponent, it's raised to a positive exponent. And then, of course, I have a quotient raised to an exponent, which means that I apply the exponent n to the numerator, and I apply it to the denominator, and I get b to the power of n over a to the power of n, and that's it. So let's apply this, this general rule that we just learned to these powers. So if I have 2 over 5 to the power of -3, so what do I do here? So let's do the first example. So I know that I'm going to rewrite this as 5 over 2. And instead of raising it to the power of -3, I'm going to raise it to the power of +3. And then I simply take the exponent and I apply it to the numerator and the denominator. So I get 5 to the power of 3 over 2 to the power of 3. And 5 to the power of 3 is 125. 2 to the power of 3 is 8. So I'm done. So that is my answer. You can even check that that's correct. Let's do the last one here. So we have a fractional exponent, a negative fraction raised to a negative exponent. So geez, it seems a little harder. But again, you're going to notice these are not that hard, really. We're following the same concept. So we find the reciprocal of the base. So same thing, find the reciprocal of the base, and then you raise it to the opposite exponent. So we're going to raise it to the power of +5 instead. Now, notice what happens here. We have a negative base raised to an odd exponent. So the rule here, we know the answer is going to be negative. So because you know the answer is negative, then honestly, you don't even need to consider, whether it goes, if the negative goes in the numerator or the denominator. Don't even worry about that. You know the answer is going to be negative. So just remember that the answer is going to be negative. And then what you're going to do is simply apply the exponent 5 to the numerator and apply to the denominator. So you end up getting 4 to the power 5 over 3 to the power 5. And then my last step here, I simply figure out what 4 to the power 5 is. We know that 4 to the power 5 is going to be 216, and 3 to the power, oh shoot, it's not 216. I have that answer wrong. It's 1024. Sorry, that was my bad. What happened there? Sorry, guys. Okay, so we have 4 to the power of 5, which would obviously be 1024. And that's going to be 1024. And this is divided by 243. So there is my final answer, right? So I simply write it as negative 1024 over 243. Now this one, to be honest with you, if you have a calculator, you can obviously figure out what 3 to the power 5 is. If you weren't given a calculator, and again, it's kind of hard right now with everything online, because I know that in some parts, there's no way of controlling the calculators, whether you use it or not, but you should be able to hopefully do these calculations without a calculator. But something like 4 to the power 5, I don't know if I would necessarily give you that if I knew you didn't have a calculator, right? But I might give you something, but you definitely should know at least the powers for the smaller numbers, right? You definitely should know, for example, 4 to the power 3 is 64. You're going to see that a lot. 3 to the power 3 is 27. 3 to the power 4 is 81. There are certain ones that you should definitely be more familiar with. So last couple examples, simplifying expressions. So what do we do when we have a larger expression and we're asked to write all of it as a positive exponent? So you're going to see these types of questions a lot. So in the first example, it seems really tricky. 9 to the power -3 times 9 to the power of 8 divided by 9 to the power 6 times 9. But really, this isn't that hard. We're applying the same rules as before. Only difference is that there's going to be some negatives. So -3 plus 8, we know that -3 plus 8 is going to give us +5. And this one right here, you don't actually see an exponent there, but remember, it's not 0. 9 to the power of 9, sorry, if you're multiplying by 9, I can rewrite that as 9 to the power of 1. And the reason I redo that is so I can actually apply the exponent laws. So I add the exponents, I end up getting 9 to the power of 5 divided by 9 to the power of 7. And of course, how can I rewrite this? Well, I know that 9 to the power of 5 over 9 to the power of 7 is going to be 9 to the power of -2. I simply subtract the exponents. But remember, since the question asked me to write as a positive exponent, I'm going to rewrite that as 1 over 9 squared, and I'm done. So hopefully that made sense so far. And what about B? Okay, these questions are a little bit tricky, but what I suggest with something like this is I would simplify what's in the brackets first. And again, there's multiple ways to simplify these expressions. And this is what sometimes gets hard with exponent laws is sometimes students will tell me, I simplified it a different way, or I went about it in a different direction. As long as the steps are reasonable and they're solid and the reasoning makes sense, that's totally fine. There's more than one way to solve these, right? So that's more than normal. So what I want to go through is this one here. So if we have 5 to the power of 3 times 2, how did I get that? Well, I simply have a power to a power. So I multiply the exponents, and 5 to the power 5 times 5 to the power 6 becomes 5 to the power 7. Apologize. So now we end up getting, now we end up getting 5 to the power of 6 divided by 5 to the power of 7, which means that we subtract the exponents. And then we end up getting 5 to the power of negative 1. And then 5 to the power of negative 1 is then raised to the power of negative 1. And this might seem really confusing, but before you even find out what the reciprocal is, I hope you realize that you can actually do something easier. You have a power to a power, which means that you can multiply the exponents. And we notice that negative 1 times negative 1 gives us positive 1. So we end up with 5 to the power of 1. So a couple more examples here. I want to go over how to deal with the sum of powers, because it's a little bit different. So if I have something like 8 to the power of negative 12 plus 4 to the power of negative 1 to the power of 2, well, there's not really much I can do right away, but I hope you realize the first thing that I can probably do is simply rewrite this as 1 over 4. So I rewrite it as a reciprocal there, and then I raise it to the power of 2, and 8 to the power of negative 2 is simply going to be 1 over 8 squared. So I simply, again, we talked about this, find the reciprocal, which is 1 over 8, and I raise it to the power of the positive exponent, which is 2, and that becomes 1 over 8 squared. Then I apply the exponent 2 to the numerator and the denominator, but again, because the numerator is 1, nothing really happens there, it just becomes 1. And then we have 1 over 64 plus 1 over 4 squared, which is 1 over 16. I now have to find a common denominator. So this actually goes back to what we talked about in rational functions, find a common denominator. It's going to be 64, which means that this needs to switch into a common denominator 64. So how do I go from 16 to 64? I multiply by 4, so I do the same to the top, the numerator there. I multiply by 4. And then I get 1 over 64 plus 4 over 64. And that means I get 5 over 64, and we're done. So simplifying and evaluating expressions. So if you want to simplify and evaluate expressions, what you're going to do first is you're simply going to multiply the powers that have the same base. And then you multiply, you multiply powers with the same base first. So we multiply the a's together. And then we're going to multiply the b's together, right? We do them separately. And then when you're done, you want to then evaluate your expression for the given for the given values there. When you're doing these types of questions, it's really important, and sometimes students will make this mistake, that they'll actually sub in the values first before they simplify. If you do that, you will a lot of times end up with a lot of calculator issues. In this example, the numbers are still relatively easy, but there are definitely some examples in the book where you have something like, a to the power of like 24, right? Times b to the power of negative 28 or something. I'm making that up. If you type that in your calculator, so if I were to, let's say the a value was, I'm making this up, but let's say the a value given to you was 3, and the expressions has something like a to the power of 24. If you take 3 and you raise it to the power of 24 in your calculator, you're probably going to get something that says error, right? And now and even that number itself is a little bit small. So maybe you need to make it a little bigger, but I'm actually going to try it myself. I just want to see. Actually, you still don't get an error. And again, I'm using my phone calculator here, but let's say I'm just going to make this bigger so you actually see a difference. 21 to the power of 24, right? So if the a value is 21, and then I raise it to the power of 24, you're obviously going to run into an issue that it's not necessarily going to work, right? So the number is too large there. So what you really want to do with these questions is simplify first before you sub it in, because when you simplify, the numbers actually become smaller, and then it's easier to work with. It's easier to evaluate, especially when you don't have a calculator, right? You want to be able to do this without a calculator. And just a reminder, I know we talked about this in class already, but keep in mind that this year is a little bit different in the sense that you probably have more access to technology to maybe assist you with the questions. You really want to remember that, when COVID is all done and we return back to classes like normal, you need to be able to do these questions on paper with a paper and pen, right? You're going to be doing this in class, no calculators, right? So you want to make sure that you know how to do this with and without a calculator, right? So especially with questions like this, if it doesn't directly tell you need a calculator, you shouldn't be using the calculator, right? And I'm relatively flexible with this. Obviously, there's some word problems that we're going to look at later on where you definitely need a calculator. But for these types of questions, you should be able to do them without, right? So first step is you're going to be multiplying the powers that have the same base. So I'm going to be multiplying the a squared. Oops, I'm going to try to keep the same color. So let's multiply a squared times a to the power negative 5. And that means I simply subtract the exponents. And then I'm going to multiply the b to the power negative 1 times b to the power 4, which means I add the exponents. So I end up getting negative 1 plus 4. So I end up getting a to the power negative 3 times b to the power of positive 3. And of course, if I'm trying to evaluate for a is equal to negative 2 and b is equal to 3, what I need to do in this case is simply replace the a value with negative 2 and replace the b value with 3. So it's similar to functions, right? We're just substituting in the values, except that this is not a function. This is just an expression. So obviously negative 2 to the power negative 3, we discussed this already. You have a negative base and an odd exponent, and this is still going to be an odd exponent there. You know the answer is going to be negative, right? So we're going to rewrite this as 1 over negative 2 to the power 3. You know the answer is going to be negative in the end, so you can always put a little reminder to yourself, this is going to be negative. And 3 to the power 3, we know is going to be 27. So then you end up getting 1 over 2 cubed, and obviously 1 over 2 cubed is going to be 1 over 8, but remember, we talked about this, the answer is going to be negative. Now I can either leave the negative in the denominator or in the numerator or in front, but I can't do all three, right? That's different. You definitely don't want to do it in the numerator and the denominator, because that means the answer would be it would be positive. So in this case, I would just keep it as I would either leave it in the denominator or put it in front. And then we end up getting, and again, you can just multiply these two numbers now. You have negative 1 over 8. So I'm going to rewrite it as negative 1 over 8 times 27, which we know will be a negative answer. And I simply multiply the numerators and the denominators. I get negative 27 over 8. And that is my final answer there. So now that we know about all the exponent laws, here's the updated list, basically what we already talked about. I'm not going to go over this because we discussed this already. The only two exponent laws I've added are the two that we just learned right now. So an integer to a negative exponent, how to deal with that, you simply find the reciprocal of the base, raise it to a positive exponent, and then you find your answer. And if it's a fraction, you follow the exact same steps, find the reciprocal of the base, which means you switch the numerator and the denominator, and you simply raise it to a positive exponent. And then don't forget that that exponent is applied to the numerator and the denominator. And that is it. Okay, guys, so best of luck. And there are all the questions there.